podcast is brought to you by LMU Munich.
Well, I would also like to thank the organizers for putting together such an interesting meeting. I'd like to tell you today about some work I did recently with David Tong and my postdoc, George Santos. Let me say at the outset that most of the hard work in this project was done by George. For 80 years after Einstein proposed his general theory of relativity, we thought it was just a theory of gravity. But for the past 15 years, we've learned that general relativity can also describe aspects of non-gravitational physics. In particular, for the past 5 years, we've learned that various aspects of condensed matter systems can be described by general relativity. This includes Fermi surfaces, non-Fermi liquids, superconducting phase transitions, and several other phenomena. And as you all know, this is a consequence of gauge-gravity duality in the limit where the bulk can be described by classical general relativity. As Sasha Polyakov mentioned at the end of the last talk, this classical limit requires that we take n to infinity, where n is usually the rank of some gauge group. And in most condensed matter systems, there's no analog of n, and it's certainly not very, very large. So in some sense, as we push more toward this ADS-CMT correspondence, things seem to be working better than expected. And I think it remains to be seen how this all plays out. Now, it's certainly a remarkable fact that general relativity can reproduce qualitative features of condensed matter systems. But can it do even more? Can general relativity provide a quantitative explanation of some mysterious property of real materials? And as I hope to convince you, there's evidence that the answer is yes. But to have any hope of doing this, we have to start to make our models more realistic. Most previous applications of gauge-gravity duality to condensed matter systems have assumed translational symmetry. And that has an unfortunate consequence. Any state with non-zero charge density will have an infinite DC conductivity. That simply follows from momentum conservation. There's no way for the charges to dissipate their momentum. A simple argument is that if you have non-zero charge density, you can simply do a boost and you get a current with no applied electric field. Now, this can be avoided in a probe approximation, as Karch and O'Bannon first showed in a classic paper. There you have just relatively few charge carriers, and their momentum can be absorbed by the large number of neutral fields. But we want to do something else. So the plan for the talk is that we're going to add a lattice, an actual lattice to the simplest models of a conductor, and calculate the optical conductivity. The conductivity is a function of frequency. Now, a perfect lattice still has infinite conductivity because the electrons aren't localized but form these block waves. So we're going to work at non-zero temperature and include dissipation. There have been some other papers by these authors where effects of a lattice have been discussed. But in most of those earlier examples, the lattice was treated perturbatively. We're going to treat the lattice exactly and find a surprising similarity to the optical conductivity in the normal phase of the cuprates. As you know, the cuprates are these interesting and mysterious materials that were shown in 1986 to have superconductivity, to become superconductors at relatively high temperatures. These are the so-called high TC superconductors. Now, before I begin, let me just remind you of the simplest model of a conductor. So suppose electrons in a metal satisfy the following equation. It's just the mass times the acceleration is equal to the force due to the electric field, plus a damping term, minus mv over tau, where tau is a relaxation time. If there are n electrons per unit volume, the current density J is just n times the charge times the velocity. And if you then apply an oscillating electric field, you find that the current, you can solve for V, find that the current is proportional to E with the conductivity sigma given by a constant K times tau divided by 1 minus I omega tau, where the constant K is basically this electron density times the charge squared divided by m. This is the simple Drude model, first proposed or derived in 1902. If you take the real and imaginary parts of that complex conductivity, you get the expressions shown on the top here. And there are two things to note. First, when omega tau is much bigger than 1, the absolute value of the conductivity is dominated by the imaginary part, and it just goes like the constant K over omega. So it falls off like 1 over omega. In a more sophisticated Fermi liquid treatment, you find that the absolute value of the conductivity goes like 1 over omega squared. The second point to note is that if we take tau to infinity, as you would have in a superconductor or even in a translationally invariant system, the real part of the conductivity becomes a delta function, and the imaginary part becomes a simple pole, k over omega. And the fact that the real part is a delta function if and only if the imaginary part is a pole holds much more generally and can be derived from the so-called Kramers-Kronig relation. Okay, so now I can tell you about our gravitational model. As I said, I want to take the simplest gravitational model of a conductor. And as Shamit said, that's basically Einstein-Maxwell theory. So we have Einstein gravity, negative cosmological constant, standard Maxwell action. And now to introduce the lattice, I'm going to couple this to a real scalar field, a neutral scalar field with mass squared equals -2 in ADS units. We're going to work in the Poincare patch with a radial coordinate z. Z equals 0 is the boundary at infinity. And then this scalar field phi has an asymptotic solution which goes like z times some field phi 1 plus z squared phi 2, etc. And we're going to use standard quantization, so phi 1 is the source and phi 2 is the response. We input the lattice by putting in a periodic source for the scalar field. So we're going to require as our boundary condition that phi 1 be an amplitude A0 times cosine k naught x. We put the lattice in only in one direction. That's for numerical convenience. And we're going to compute the conductivity only in the direction of the lattice. We, of course, want to work at finite temperature. So we're going to add a black hole. We also want to work at finite chemical potential or finite density. And to do that, we set the time component of the vector potential equal to a constant mu at infinity. That's the chemical potential of the dual theory. And then we numerically solve Einstein's equation, look for solutions which have smooth horizons, which are static, translationally invariant in the one direction where we don't have the lattice. But the solution will clearly depend on two parameters now. The direction, well, two coordinates, I should say. It's going to depend on the direction x, where we have the lattice, and the radial direction z. And the problem requires that you solve 7 nonlinear coupled PDEs in 2 dimensions. This is one of the points where George Santos's expertise was crucial. So he solved those equations and gave us these beautiful plots. So here is the scalar field in the fully back-reacted solution. This is a rather cold black hole. It has T over mu equal to 0.1, and this wave vector for the lattice equal to 2. So you have 2 peaks. Here's a plot of phi as a function of x, the lattice direction, and this coordinate going back is our radial coordinate z, where infinity is up here in the front, and the horizon is in the back at z equal to 1. So you notice that the scalar field starts to rise and then starts to fall toward the horizon. It's beginning to rise because the operator dual to phi is a relevant perturbation, which is sourced, so it starts to grow. It starts to fall because the average source is 0. We have this oscillatory source, so the scalar field is becoming large and positive in one region and large and negative in another. and as you move into the infrared, the gradient energy starts to dominate over the potential energy, and the scalar field starts to come down. The solution at 0 temperature would in fact have the scalar field go uniformly to 0 at the horizon. Okay, so here's another plot. On the right-hand side, I've stripped off 1 power of z so that you can see the lattice. So here is now the lattice that we input as our boundary condition for phi, and it's falling off as you approach the horizon. On the left-hand side, I'm showing you one of the metric functions. This is a metric function, again, as a function of x in this direction and radial coordinate z going back. And the main thing you notice is that it has twice as many peaks. Well, that's what you expect because the metric feels the scalar field through the stress tensor, and the stress tensor is quadratic in phi. So the effective lattice imprinted on the metric, in fact, has a wave vector equal to 4. It's half the wavelength. Okay, so now we want to calculate the conductivity. And as you know, to calculate the optical conductivity using linear response, you have to perturb your black hole. In the simple case, when we had translational symmetry, there were some equations decoupled, and you only had to solve a couple of them. Here, everything couples, and you have to solve everything. So we perturb the metric. So you have the background metric, which is the lattice I just showed you, and there's a linear perturbation. The Maxwell field has a background value and a perturbation, which I'll call B, and the scalar field has a background value and a perturbation. The boundary conditions we impose are the usual ones. We want ingoing wave at the horizon. That's to get the causal response, causal Green's function in the boundary. We require the metric perturbation and the scalar field perturbation to be normalizable at infinity, falling off with no sources. The time component of the vector potential perturbation also doesn't have a leading term. We're not going to perturb the chemical potential. That was constant in the original solution, and we're going to keep it constant. But what we are going to do is we're going to add a source to some spatial component, well, actually the spatial component along the lattice, B sub x. And this leading term just induces an electric field in our boundary theory. So we apply the electric field, and then we look at the subleading correction here. This order z correction is the induced current. Okay, so the conductivity is determined by Ohm's law, and it can be given in terms of the perturbed Maxwell field. So if I define little f to be just the curl of our perturbed vector potential, then the conductivity, which in general is a function of omega and x, is given by the limit as you go to the boundary of fzx over fxt. Fzx is just the induced current. It picks out that first subleading term in the vector potential, and fxt is just the applied electric field. So this is the conductivity, but we applied a homogeneous electric field, and we're interested in just the homogeneous part of the conductivity. So that's what I'm going to be plotting in the next plots, and that's what I'll call sigma of omega. Okay, so before I give you the results with the lattice, let me remind you what the results without the lattice look like. So here is a plot of the optical conductivity computed holographically from just the Reisner-Nordstrom ADS black hole, a rather cold black hole again, T over mu of about 0.115. The real part of the conductivity is on the left, imaginary part on the right. The real part approaches a non-zero constant at large omega. That's simply saying that you have basically a conformal field theory. At small omega, there's a dip, the conductivity comes down, and most importantly, there's this delta function, which I argued had to be there by translation invariance. And that delta function in the real part corresponds to this pole in the imaginary part of the conductivity. Now you apply you solve the problem with the lattice, you perturb the lattice, compute the conductivity, and you find this. Okay, so the main thing is that the delta function is smeared out. This is what we were looking for, and this is what we find. At large frequency, there's no difference. So this black dashed line is a homogeneous result, and the conductivity with the lattice looks like the homogeneous thing, except when you come to small omega. And at small frequency, the conductivity rises and actually has a finite limit, finite DC limit. The delta function is broadened, and corresponding to that, the pole is no longer there. The imaginary part starts to rise and then drops back to 0. So what I want to do now is to zoom in on this low frequency region, and I'm going to do it in 2 steps. I'm going to first zoom in to the very low frequency region and then look at this sort of fall off as we approach the homogeneous case. So if you look at very low frequency, so this is omega over t between 0.1 and 0.6. This is the real part, this is the imaginary part, and what we find is that both the real and imaginary parts of the conductivity computed from general relativity agree exactly with this very simple Drude form that was derived 100+ years ago. So you might think this is a 2-parameter fit. We fit all these points to k and tau, but in fact k is exactly the same to our numerical error to what you would get in the homogeneous case. So k we can read off as the pole in the imaginary part of this, in the homogeneous case. That's related to the electron density. We get exactly the same k here, and all that we're actually fitting this just to tau. And we can choose tau to match all these points. And it's not just for one case. We varied the temperature, we varied the lattice spacing, and in every case we get a nice simple fit to this Drude form of the conductivity. It seems very surprising that general relativity would know anything about this Drude form of the conductivity, but what's even more surprising is what happens when we look at slightly larger frequency. Then we find this sort of emergent scaling regime. If we look at slightly larger, this is now plotted the absolute value of the conductivity as a function of frequency, and the data is very well fit by a form which is a constant b over omega to the 2/3 plus another constant c. The imaginary part, or sorry, the argument of the complex conductivity is relatively constant and about 65 degrees over this range. Now, this exponent, this 2/3, is not something that we put into the model. Again, we've changed various parameters, and we still get 2/3. To make that more clear and to also show this power law more explicitly, let me draw this on a log-log plot. So here I've plotted the log, well, the absolute value of the conductivity minus this constant offset on a log-log plot with the frequency. The straight line means that we have a power law. The fact that these straight lines are parallel means that you get the same power law. And on the left, I'm showing our results for different wave numbers. So this is k naught equals 1/2, 1, 2, 3. The lines are perfectly parallel. We're getting 1/2 in all cases. Here we change the temperature, and we're getting the same, we're getting the same 2/3. We're getting this 2/3 exponent in all cases. So it's not put in, it's coming out of general relativity. Now I told you at the beginning that the Drude model doesn't predict 2/3, it predicts a 1 over omega. And the standard Fermi liquid theory predicts a 1 over omega squared. So have we ever seen 1 over omega to the 2/3 before? And the answer is yes, in nature. Okay, so here's real data. This is data taken by Van der Merel and his group on the normal phase of this cuprate, bismuth, strontium, etc. This is usually called biscope. And here again, they plot the absolute value of the conductivity as a function of frequency for various temperatures. And you see that, well, actually, this early region is fit by the Drude form. So that's also in agreement. But what's more interesting is that there is a clear power law fall off of the conductivity. And when they measure it, they get omega to the minus 0.65. So I don't think, I mean, our numerics is not good enough to distinguish 2/3 from minus 0.65, and I'm not sure their data is good enough to distinguish minus 0.65 from 2/3. But in any case, the agreement is really striking. In the theoretical condensed matter literature, I don't think there's an agreed upon explanation for why this optical conductivity has this 1 over omega to the 2/3 fall off. If you ask about the phase, the measured phase on this BISCO compound is given here. It's constant over this range of frequency at just 60 degrees. And I'll remind you that we get a value which varies somewhat, but is about 65 degrees. I should mention that our phase actually does vary slightly with K0. Unlike the power law, which is very rigid, very robust, this phase has slight variations and varies a little bit. I should say, though, going back to here, that there are, of course, some differences between what we calculate and what is measured. First of all, there's no analog of the offset. We had b over omega to the 2/3 plus a constant c. They get a pure power law. Okay, so they don't see any sign of this offset. And second of all, you see that when they vary their temperature, these curves are exactly the same, which means that the coefficient of the 1 over omega to the 2/3 is temperature independent. And if you go back and look at our data, here we vary the temperature and we do see a slight change, slight temperature dependence of our coefficient. So those are a couple of differences, but still the exponent is coming out right and the phase is looking pretty good. So the next thing you can ask is, what about the DC conductivity? As we heard earlier this afternoon, a characteristic feature of a lot of these cuprates is that there is this strange metal region above the superconducting temperature in which the DC resistivity scales linearly with temperature. We have the DC resistivity as a function of temperature, so we can plot it now, and what we get is a mess. Okay, so here is our plot, a row. This is the DC resistivity as a function of temperature, and these curves correspond to different lattice spacings. So we are clearly finding that the resistivity is not as robust as this optical conductivity, and it depends on the lattice spacing. Okay, when we first saw this, we were very confused. In fact, the first one we did was K0 equals 2. And we're actually very happy because that looked rather linear. And then we had the bad idea of checking other values of the lattice spacing, and we came up with this. But then we remembered there was a paper actually just a few months earlier by Hartnell and Hoffman in which they studied the DC conductivity in the case when you had this locally critical region characterized by ADS2 across R2. And Hartnell and Hoffman showed that at low temperature, this DC resistivity can be extracted from the 2-point function of the charge density evaluated at the lattice wave number. And they came up with a formula that the resistivity should scale like a power of the temperature, where the power nu depended on the lattice wave vector. So we tried it, and it works beautifully. So what I've done now is I've taken the DC resistivity we compute, divide by the scaling that Hartnell and Hoffman predict, and plot now the ratio as a function of temperature. So the data is indicated here, and we've done an extrapolation of the data by some like 4th order polynomial fit, and they all reach nice finite non-zero values. If our scaling had been different, these curves would be either going off to infinity or going down to 0. So the fact that they all reach nice finite non-zero values means that our data is in good agreement with this Hartnell and Hoffman result. Okay, so now we can go further and we can say, what about ADS5? The calculation I showed you before was ADS4. this is appropriate for a 2+1 dual theory, which is the right arena for describing the cuprates because the conductivity is associated with these copper-oxygen planes. But we can say, what happens if you had a more isotropic, strongly interacting condensed matter system? We redo the calculation in 5 dimensions. We find qualitatively the same result, a Drude behavior at low frequency, then a transition to a power law fall-off regime, except now the exponent is different. So the exponent does depend on dimension, and we find that it falls off like 1 over omega to the root 3 over 2. And it would be great to find a 3+1 analog of the cuprates to compare this to. So far, I haven't been able to find one. Just to show you, this exponent is again robust, not something we put in. Here's the log-log plot as before. Lines are very nicely parallel. Okay, so then we went on and we checked a few more things. And so here is some further evidence for this lattice-induced infrared scaling region. We repeated our calculation for an entirely different lattice. We threw away the scalar field, and we said, just in Einstein-Maxwell, we can just ask that our chemical potential be a periodic function of x. This is sometimes called an ionic lattice. We redid the calculation for this kind of lattice. We find exactly the same result, again with a power law fall-off with exactly the same exponent. So this is again confirming that this exponent of 1 over omega to the 2/3 is not something we put in. Then we looked at the thermoelectric coefficient. When you apply electric field, you not only generate electric currents, you can generate a heat current. So we looked at that heat current and found that it also has a power law fall-off at intermediate frequencies with an exponent, which in this case turned out to be 1 over omega to the 0.8. Needless to say, this is not something we can compare with experiment, because experimenters have a hard time measuring heat flow oscillating between directions at at high frequency for some reason. Okay, so let me summarize. We've constructed the gravitational dual of a lattice. We've actually done it for 2 different lattices, and this is fully back-reacted in general relativity. We perturbed the black hole solutions and computed the optical conductivity. We found a simple Drude behavior at low frequencies, and then a transition to this intermediate power law with an exponent that agrees with the normal phase of the cuprates. Finally, we calculated the DC resistivity and found that it scales like a power of the temperature, but the power depends on the lattice spacing in good agreement with the analysis of Hartnell and Hoffman. And I'll stop there. Thank you.
Any questions?
Eva has a question.
So as you said, it seems really interesting how it's robust against changing the lattice size, but there might be other parameters like the dynamical critical exponent or maybe running scalars and so on. I know it's a hard numerical calculation, but do you know if it's robust against all those things?
We do not know. We've only looked at the Einstein-Maxwell theory in the bulk, but you're right. It would be a good question and something we will look at in the future to modify it with dilaton couplings and see if that changes the exponent.
What was the gravitational expression for the Drude time? Tau?
Tau?
Yes.
Well, tau is just read off. So we compute this optical conductivity, and you fit it at low frequency.
There's no intrinsic meaning.
Yeah. So you notice that it takes exactly this form, and you read off tau.
So if you take the gravitational model of superconductivity on one side, and on the other side you take the fact that superconductivity involves actual particles moving around, and then you try to compare them and analyze them, will you be able to come up with the model of G mu nu in terms of those particles moving around?
Well, it doesn't quite work that way. I didn't talk about the superconducting phase here, but as you know, there are holographic superconductors, and one of the things we're doing now is putting in the lattice into those holographic superconducting models to see their effects. But well, at least the local properties of the dual theory, the currents and everything, are read off from asymptotic properties of the bulk solution.
Yes.
Is there any understanding why it works so well? Is this kind of new universality or what?
No, that's another thing we're working on, to really get some sort of analytic understanding of why this is working. But at the moment, it's just data, numerical data.